Welcome back. This is lecture 9 in this course Mathematical Tools for Cognitive Sciences. The topic of this lecture is logarithmic functions. So, if you recall, in the previous lecture I introduced you to exponential functions and also the standard exponential function with the term e. Okay. So, let me just take you back briefly to exponential functions. So, an exponential function is a function of this form where a is called the base and x is the exponent. Okay. So, here the variable is actually x, a is some constant. Okay. So, this is a function of x, okay. And in a standard exponential function, this constant base is actually e, which has value somewhere around 2.31 or something. It is called Euler's term, right. So, this standard exponential function is e to the power x. Okay. Now, here this base is greater than 0, x can take any real value, right, and the graph of these functions looks something like this. So, this is how typically graph of an exponential function looks like. You can make slightly more curvy, right. So, the main thing with the exponential function is that this is x axis, this is y axis, right. So, it in the beginning it increases slowly. So, as the value of x changes, value of y changes by a very small difference. So, it is almost, you can see it is almost flat, it is almost parallel to x axis here, but as the value of x keeps on increasing, the value of y starts increasing rapidly. So, actually the rate of increase of y is changing. Okay. So, initially the rate of increase of y with respect to x is very small, then the rate of increase in y with respect to x increases here slightly, and in the later part the rate of increase of y with respect to x, it is very high in this region. Right. So, the rate of change in y with respect to x is changing and it is increasing as the value of x increases, right. And we also discussed the function with which this rate changes. That function also remains the same for exponential function. The rate with which the value of y changes with respect to value of x, that function is also e to the power x. Okay. However, if you have a negative exponent, so let us say function is a to the power minus x. Okay. In that case, this graph would look like this. Okay. So, this is an exponentially decreasing graph. We call this graph exponentially increasing. Exponentially increasing graph, this is exponentially decreasing graph. Now, the rate with which y changes with respect to x, that rate is also decreasing. Okay. So, these were exponential functions. Now, let us take any exponential function f of x equals to a to the power x. What are the constraints? A greater than 0, x could be, let us say, any real number. What are the constraints on f of x? What is the codomain of this function? F of x should be greater than 0, right. The domain is that x can take any real value, y f of x can only take positive value, and this a should be greater than 0. So, these are the constraints. So, this is an exponential function. How about an inverse function of this exponential function? So, what would be the inverse function of this? Okay. What would be the inverse function of this exponential function? Okay. Now, for inverse function, let us first try to visualize it in the graph, how the inverse function would look like. So, how the graph of a to the power x looks like? So, a to the power x graph would look something like this. This is f of x equals to a to the power x. You have x here, you have y here. This is how the graph of exponential function e to the power x looks like. Depending on value of a, it would cut the y axis, sorry, it would have a certain rate of increase. Now, how do we draw the graph of the inverse function? Remember, we discussed this in one of the lectures, that seeing the graph of a function, you can always draw the graph of its inverse function. How do we do that? Well, you just need to first put a line. Which line? Y equals to x. So, just need to put this y equals to x line. So, that is it, something like this. Okay. To make things simpler, let us say this exponential graph is going like this, and this is y equals to x line. This is y equals to x. Okay. Now, the inverse function would be a mirror image of this function f of x along this line. So, if you place the mirror on this line y equals to x, so whatever mirror image you would see, that would be the graph of its inverse function, and that mirror image would be something like this, a line which becomes asymptote at the y axis, right, and it would cut the x axis at same point where it cuts the y axis. Where does this line cuts the y axis? At 1, because when x equals to 0, the value of exponential function is 1. So, now this line will cut the x axis at 1, and then it will keep on going like this, and at some point it would become almost parallel to x axis, because also this in this exponential function, this line also becomes parallel to y axis at some point. So, this line would become parallel to x axis. Okay. So, this is the inverse function of the exponential function, okay, and there is a name for this inverse function. This function is called a logarithmic function. So, in general, the inverse function of an exponential function is a logarithmic function. And what is exactly the form of this logarithmic function? For that, we need to understand the rules of logarithmics. You already have seen the rules of exponents. Now, there are rules of logarithmics which we'll need to take a look at, right. So, these are also identities. Okay. So, logarithmic functions. So, suppose you have something like a to the power x. Okay. If you take log of this a to the power x, then this term can be written as x into log a. Okay. So, this is the first rule that logarithmic functions follow. Log of a to the power x equals to x into log a. Okay. Another important rule is this, that these logarithmic functions have a base similar to exponential functions. So, exponential functions always have a this base, right, a constant base, and we take some constant base to the power x. Similarly, logarithmic function also have a base which is written actually here. So, let us say a, let us say the base of this function is a. Okay. So, if it is log base a, and if you take log of some quantity a, right, basically same quantity which is there in the base, right. So, log base a of a would be actually equal to 1. Okay. Log base a, if you take log of a, where the base of logarithmic function is a, then it would be 1. Similarly, for example, log e, and if you take log of e, this would be equal to 1. So, that is another rule. So, log base a, if you take log of a where the base is a, then it would be equal to 1. Okay. So, by the way, if you apply these two rules, so let us say if you take log base a, and if you want to apply it to a to the power x, then according to identity 1, it should be x into log a. Okay. So, it would become x into 1, this would be 1. So, this term would become x. Okay. So, log of a to the power x can become x if the logarithmic function has base a. If it has a different base, then it will not be equal to x. Okay. Now, there are more rules which we will discuss in a while, but with these rules, let us try to derive the inverse function of an exponential function. Okay. We might need some more. So, okay. So, let us say yes. So, if you have, let us say, log of, okay, I think this would be enough to derive the inverse function. Okay. So, let us go back to the exponential function. Exponential function was a to the power x. Now, what were the steps that we follow to derive the inverse function of a function? Well, we first thing we try to do is, let us plug in, rather than f of x, let us write y equals to a to the power x, and now we will solve it for x. Okay. So, we want to find out what is x equal to. How do we do this? What if I apply a function log a on both sides? So, I take log a y and I take log a of a to the power x. Now, from one of the rules of logarithmics that I discussed, what would be log a of a to the power x? It would remain x, and on this side you will get log a y. Okay. So, x is equals to log a y. Now, in the final step, we will replace x by f inverse x and we will replace y by x. So, this is the inverse function of our original function f of x equals to a to the power x. So, its inverse function would be log base a, and so basically log base a of x. Okay. So, you can use this as a general rule. So, whenever the function is a to the power x, its inverse function would be log base a of x, right. So, when this base in the exponential function changes, the base of the logarithmic function also changes, right. So, if you want to find out for f of x equals to e to the power x, then the inverse function would be log base e x. Okay. There is a name for log base e, it is called natural log. It is called natural log, because similar to this e, the log base e also has some interesting properties. So, that is why it is one of the useful logarithmic functions. So, this is what we use typically when we will be using it in rest of the course, right. So, you can also write log base e as ln, which means natural log ln x, or simply you can write it as log x, right. So, if you do not write any base, by default it is usually understood as log base e. Okay. So, that is the inverse function of an exponential function. Okay. So, the graph of logarithmic functions we have seen before, it looks like this. We draw the graph of the inverse function, looks like this. So, in your calculators you would always have this logarithmic function. So, you can always find out what would be log of 1, log of 2, log of 3. So, for example, if you find out log of 1, it would always be 0. So, basically this is this point. Okay. If you try to figure out log of, let us say, e, if base is e, then it would be 1. Okay. And so, which is basically here, and if you find log of any value close to 0, let us say log of 1 by 100, okay, then this would become a negative value. Okay. So, log of, let us say 0.01 would be a negative value. Okay. And there is a reason for that, you can figure it out yourself. What would be log of 1 by 100? You tell me. Let us apply one of the rules that we just discussed. Can we write this in form of exponent 1 by 100? So, 1 by 100 is like 1 divided by 10 to the power 2, 1 divided by 10 square. So, it would be log of 10 to the power minus 2. This is how you can rewrite it. So, this is then basically minus 2 into log 10. Okay. So, log 10 would be some positive number, okay. Minus 2 into log 10 would be some negative number. So, log of anything that is less than 1 would be a negative number. What would be the domain and codomain of a logarithmic function? What would be the domain? What values x can take? Now, interestingly, the domain of this function would be same as codomain of the exponential function. What was the codomain of the exponential function? That y cannot take any negative value or not even 0, right? Y has to be positive. The same would follow for domain here, right? So, x has to be greater than 0. So, a logarithmic function is not defined when x is 0 or x is negative. So, x has to be greater than 0, and the function can take any real value. X has to be greater than 0 and function can take any real value. That is how the logarithmic function behaves. Now, let us take a look at some rules of logarithmic functions, right? Rules or identities. Two rules we have already seen. Let us go to third. If you have two variables, let us say x plus y, and if you take log of x plus y, okay, sorry, not x plus y, let us say two variable x into y, which are multiplied with each other, okay, log of x into y. These could be two functions as well. You can also write, let us say you have two functions f of x or g of x, okay, that does not matter. Let us say any two variable x, y, okay. Then if these are multiplied log of x into y, then this would be you can be rewritten as log of x plus log of y, okay. This is how you can rewrite it. Log x y equals to log of x plus log of y, okay. Fourth, if you have log of x divided by y, can you tell me what would be, what it would be equal to? Can you simplify this? Log of x divided by y, it should be log of x minus log of y, okay. Why? Because you can think of it as x multiplied with y to the power minus 1. So, it would be log of x plus log of y to the power minus 1, which would be minus into log y, okay. Also, this you have already seen. If you have log x to the power something, let us say a, so this can be rewritten as a log x, okay. Sixth, if you have log of, that is a log base is a and you have a to the power x, okay, log of this exponential function, you can, this can be rewritten as x, okay. Similarly, if you let us say take exponent of log base e, or let me just write log, but I mean natural log here, e to the power log x, okay. This would also be equal to x, but the thing is that x can only take positive values here, okay? That is the constraint. So, these are rules for logarithmic functions. These two, this is the important one which we often use, right. Okay. Let us apply these, let us solve some problems, okay. These are our in-class exercises. Suppose you are given log x cube equals to let's say 9. Okay. Solve this equation for x. What would be value of x if log of x cube equals to 9? Let us do some more. So, let's say log three x square plus log e cube let's say minus log e cube equals to 1. Can you solve this equation? Consider all logs natural logs. Third, let's say you have log of x square by 9 minus log of x by 3 equals to 1. Okay. So, try to solve these three problems. Let us try them one by one. You can stop the video and try to solve them. These are simple problems. Let us begin with first. Log of x cube equals to 9. We need to solve it for x. Okay. First, we can simplify this term log of x cube. That should be our approach when we are dealing with equations which have logarithmic and exponential functions. We should first try to simplify the term. Okay. So, log x cube can be simplified as 3 log x. This is equal to 9. That means log x equals to 9 by 3, 3, right. That means x would be equal to e to the power 3. Okay. And you can compute this number. This would come around, let's say 9, 10 or something. Okay. So, that is our solution. Second, log 3x square minus log e to the power 3 equals to 1. Okay. Well, what would be log e to the power 3? We can simplify this. What would be log e to the power 3? It would be just 3, and this is equal to 1. So, log of 3x square is actually 4, and what would be log 3x square? So, there are two terms multiplied here, 3 into x square. So, it would be log 3 plus log x square, and this is equal to 4. Okay. So, this is also some constant. So, we can write log x square equals to 4 minus log 3, and you can solve this if you want. Now, here you have log x square, which can be written as 2 into log x equals to 4 minus log 3. So, log x is actually, if you divide it by 2, 2 minus log 3 by 2, x is exponent of 2 minus log 3 by 2. So, that is how we have solved it for x. Let us solve the third problem. Log x square by 9 minus log x by 3 equals to 1. Log x square by 9 minus log x by 3 equals to 1. Okay. You see some similarity in this term and this term. So, let us try to solve for that. Log x square by 9 can be written as x by 3 whole square minus log x by 3, this is equal to 1. Okay. This can be rewritten as 2 log x by 3 minus log x by 3 equals to 1. This is 2 log x by 3. Okay. One thing you can simply do is, because this is 2 log x by 3, this is log x by 3. If you subtract, it would be just become log x by 3, which is equal to 1. So, x by 3 can be written as e to the power 1, okay, and x is then 3e. Okay. So, that is the solution. Okay. So, this is how you can solve equations with logarithmics. Okay. Now, in the next lecture, I will give you equations with both logarithmic and exponential functions, and we will see how to solve equations containing logarithmic and exponential functions. So, we will do some more practice with logarithmic and exponential functions, and we will also try to derive some of the identities based on some basic identities we know about logarithmics and exponential functions. And I will also give you an exposure to how these logarithmic and exponential functions are useful for, let us say, for studying cognitive sciences, because they are used in some of the models of perception or memory. Okay. All right, I will stop here and see you in the next lecture. Thank you.